Yeah.
Okay.
We can start. More people will come. Yeah. Okay, so today we are very happy to have Peizhi from Rutgers University. Again, he's based in Maryland, and then we first supposed to be doing before moving to Rutgers. Today he's going to tell us about new semiconductor devices for that language. So yeah, thanks.
Yeah. Thank you. Thank you for the invitation, and thanks for the nice introduction. And today, as I listed here, I'll be talking about using new semiconductor devices to look for dark matter. And this is working in collaboration with people listed here. So we have Daniel, postdoc perimeter, Ruben, faculty at Stony Brook, Muku, now a postdoc at UC San Diego. And we also collaborate with a bunch of experimentalists from sensor collaboration, like Javier, Guillermo, Miguel, and Show, those from sensor collaboration. So let's get started.
So the second paper is not alphabetical order.
Yes, there's some tricky things going on there because in collaboration with experimentalists. Yeah, you noticed that, yes. Okay, so the topic today is dark matter. Let's give a very brief introduction about dark matter. We have evidence for dark matter across many scales. For example, from the galaxy scale all the way to galaxy cluster and the largest scale we can observe today, the cosmic microwave background. So far, what we know about dark matter is like 85% of total matter density, 27% of total energy density of the universe is in dark matter. So it's a huge amount of energy density. However, the current evidence for dark matter is only gravitational. That means the particle nature of dark matter is unknown. And that actually is good to give us a lot of theoretical opportunities to study different types of dark matter models in different mass ranges. And here, you might already see from many talks, that this is the axis of allowed dark matter mass. From the left end, 10 to minus 22 eV, that's the candidate for fuzzy dark matter, and all the way up. And between GeV and 100 TeV, there's a famous WIMP dark matter candidate. And if we incorporate it with SUSY, so that can address both Planck-Wake hierarchy problem and dark matter. So that's why people are talking about that a lot. Also, between PeV and mid-eV, there is QCD axion, which can address both strong CP problem and also a dark matter candidate. And that's another hot topic and another good dark matter candidate. Today, I will not talk about all of them, but I'll focus on this range called sub-GeV dark matter. And that is the main focus of today's talk and about later how to probe them. Then the first question is, what are the models can predict sub-GeV dark matter? Actually, there are many models. So here I give you one example. It's called the dark photon model. So to this audience, probably I will not give much introduction to it. I just, in short, it's we add the U1 massive U1 field. We call it A prime or dark photon. That kinetic mix with standard model photon with the kinetic mixing parameter epsilon. But we don't like a pointer or stick that I can know if then. Or I can just use my pointers to see it. So this is a kinetic mixing term with the epsilon parameter. In the specific model we want to discuss today, the dark matter is the chi field. You add additional dark fermion coupled to A prime through that coupling here. So in short, we have dark matter chi coupled through a dark photon as a mediator. And now in this talk, I consider it to be light. Light meaning the mass of dark photon is much smaller than the momentum transfer. So effectively, its mass is a long range force. So that is what we consider today. So if we want to have some diagram in mind, so that is the diagram drawn on the left, where dark matter chi coupled to standard model particles like electron through this mixing through here with epsilon prime here. So all the diagram will be done by epsilon, which we always choose to be very small. Another question is, can we get the right radical abundance through this model and also evading other constraints? Yeah, there is a well-motivated mechanism called freezing mechanism, which means that, so it's also through this diagram, but going from bottom to up. The assumption is initially there's no dark matter abundance, only standard model bath. But through this process, dark matter will be gradually produced through standard model bath. But since this rate is very small, it's never in equilibrium. It's gradually growing. In the end, reach the radical abundance we observe today. So this is called the freezing mechanism.
So buried in this assumption is that these 8 primes were never present in either?
In the universe,
Yeah.
depending on what is the GD there. So what in the end is the phenomenologically relevant for dark matter abundance is the combination of epsilon and GD, and so that gives the radical abundance. If GD is small, then A prime will be one is very small.
You're assuming you have a thermal bath. Right?
No, there's no.
So then if you
Standard model is in some equilibrium. Standard model in some equilibrium, but dark matter no.
yeah, but also A prime is not in the thermal bath.
Yeah, no.
That's justified because if you remove the chi particles, then the limit of MA prime going to be 0 with the susceptibility because
Well, it depends how you create your thermal bath. I mean, you're implicitly assuming that whatever it
if
is,
this was on the case,
that's what I'm saying.
Also, in the not for sensitive, but in the MA prime more massive case, you get more interesting regions of parameter space, like symmetrical freeze zone. That's where you don't have
Thank you.
but not for.
Also, another
Sure.
sort of tangential question, but like, so you said the relevant combination is epsilon.
Yeah, to some
GD.
part, yeah.
Like that's the relevant coupling to the standard model, but
Yeah.
self-interactions are just set by GD. So
Yeah,
if
so-
you do like
yeah.
self-interaction bounds on dark matter, set constraints on
That's
GD.
GD.
alone.
Yes. So yeah, I'm saying the combination to get the right radical abundance. So you can play with GD to reduce abundance of A prime in the early universe. Yeah, that's my point. Yeah. Yeah.
typically need both epsilon and G.
Oh, they do both.
Okay, yeah, let's move on for the main focus of today is how to look for those dark matter. And so there are, I also list like basic assumptions, how we detect dark matter. So there's a program of detect dark matter on Earth in the labs called the direct detection. And one of the big assumption is that first we assume dark matter has interaction with our standard model particles more than gravity. So that's a big assumption, which does, because like the model we have before, if you assume that model, it has more than gravitational interaction with us. So that's a big assumption here. Second, since these cross sections are, as we see later, will be very low, so it's a very rare event detection. So we need a very clean environment and a good sensitive detector to look for it. So here is a cartoon picture of how the detecting environment. So we put a detector in some kind of shielding. So this shielding could include some kind of heavy mountains or deep underground, or some heavy metals that can stop some like radioactivity. And the dark matter will come in to deposit some energy into your detector. Then we just wait for dark matter to come. So that is the basic idea behind direct detection. So how does that work in reality? Depending on what is the mass of the dark matter and what type of interaction with our standard model particles. So here I give you like a overview of what are existing ideas, not all, but typical ideas to detect dark matter. So let's start with the heavy dark matter. Let's assume dark matter heavy and has a lot of kinetic energy and can deposit more than keV energy to your target or to a detector. This is a detector. So here I use a magnifier to see roughly what kind of scale this type of interaction can probe. For this large energy transfer, or in other words, large momentum transfer, we are probing very small scales. And what we will probe is around the nucleus inside your target, inside your detector. Then we can look for dark matter nuclear scattering. So that is called nuclear recoil processes. So the cartoon picture is shown here. When dark matter comes, hits a nucleus inside your detector, nucleus recoils and generates some signal. And we can estimate what is the momentum energy transfer in this process, which is simply by giving this classical formula, where Mn is the nuclear mass, Chi is the dark matter mass. So on the right, I showed you a cartoon picture of a current like this WIMP searches. We have a big tank of some noble liquid, for example, liquid xenon. And when dark matter hits the xenon nucleus recoils, generate prompt signal. And then at the same process, ionize a lot of electrons, and those electrons be drifted to the surface, generate S2. So you have a correlation of this S1 and S2. You will call it a dark matter event, and the threshold for this is order KeV. So that is the idea behind all these WIMP searches. And what we found, this is our summary plot for that. Of course, so far we haven't discovered dark matter. Otherwise, we'll not talk about this topic today. And this is, by the way, what we got is the exclusion plots. So all the regions above the various curves are excluded by the corresponding experiments. And so there's some x-axis dark matter mass in the unit of GeV. Y-axis is the dark matter nucleon interaction cross-section. So there's some universal behaviors at large mass, which is just set by parallel to this line, which is just set by the number density of dark matter. Because we know the energy density of dark matter, this rho dm in our local labor, solar labor, is some fixed number. And once your dark matter mass is larger, the number density or the flux gets to go down. So that's why the lose sensitivity like this at high mass. There's another interesting feature at low mass is seems like all the curves were like losing sensitivity around the field GeV very quickly. So that is the threshold effect. I think that's one of the important effects I want to discuss today is the threshold. So because we mentioned the threshold for this type of search is order KeV, we can use this simple estimation of energy transfer for nuclear recoils. We can see that for this typical mass or below a field GeV, the energy transfer quickly go below KeV. That means if you go lower mass, you are really drop below the threshold. You will not see any, you don't have any sensitivity. By knowing that, you will say, okay, then how can we probe to a lower mass? So that means we have some lower threshold detectors or some other processes can give a larger energy transfer. Then let's look at other targets. Let's say we're in our target, the semiconductor, and we're looking for energy transfers order EV scales. What we'll see here, because now we're probing like larger scales, what the dark matter can probe is not just the nucleus, but actually we can see the crystal structure and the band structure of those electrons. In this case, we can look for dark matter electron scattering, dark matter directly interacting electrons. In this case, they can ionize electrons from the valence band to the conduction band to generate electron hole pair, and we can look for those. And this is the class of models or ideas we call it the electron scattering, dark matter electron scattering. There are several advantages of considering dark matter electron scattering compared to nuclear recoils. So one thing is about just looking at energy transfer. So energy transfer in electron recoils can, in principle, access to the whole kinetic energy of dark matter, which is m-chi-v squared, because it's non-relativistic, which can be much larger than the energy transfer in nuclear recoils when m-chi is small. You can see this drop very quickly when m-chi is small. So that's a big advantage. So you can imagine it like electrons are like ping pong balls, where nucleons are like bowling balls. And also now dark matter is also light, like ping pong balls. So it's more easy to transfer energy from ping pong ball to ping pong balls instead of ping pong ball to bowling balls. So that's why we consider electron recoils. And the signals, as I mentioned before, are electron hole pair creation. And the threshold to create the electron hole pair is the band gap of the semiconductors, which is typically ordered EV scale. So this kind of idea has been realized in many, many experiments. So here I showed you two pictures of the real experiment following this idea using semiconductors, and we call it tabletop experiments because they are small scales. You can really see the active mass for the sensor is like 10 centimeter times 1 centimeter, and the super centimeter HEV is 1 centimeter cube. So you can really put them in your hand. So it's a small scale tabletop experiment. And the active mass is around 1 gram. Just to draw a comparison, how that dramatic change from the WIMP searches, here I showed you the xenon one-ton WIMP detector, which is a big tank of liquid xenons. It's a 1 meter tall big tank of liquid xenons, weighs a few tons of liquid xenon in it. So it's really a big paradigm shift from the WIMP searches to sub-GeV dark matter tabletop experiments. Then you might wonder, how good will this do with this just 1 gram tabletop experiment? actually it's amazing that it can do pretty well. So here is the result from Sensei collaboration, which published 2020. And this is the execution plot similar to what we discussed before, but now notice that x-axis is the unit of MeV instead of GeV before, and the y-axis is the dark matter electron scattering cross-section instead of nuclear cross-section. And all these shaded regions are excluded by Sensei. So first I want to draw attention to the threshold here. Now we can go down to a threshold of order 1 MeV. That is, as we estimated, we can understand it by this formula, because in principle, we can access to the whole kinetic energy of dark matter. If we have a threshold down to 1 eV, which is the band gap of silicon, where they use, you can probe dark matter down to MeV scale. So that's why you have a threshold down to MeV scale of dark matter. And second, there's orange line now labeled by freezing. So that is our theory target. We can get right radical abundance through the freezing mechanism I told you before, which if you stay on this line, you can get right radical abundance. So that is our theory target. It's quite amazing that in this model with the light mediator I mentioned before, it's pretty close to the freezing target, but of course not yet, but pretty close. Because it's quite amazing that for this 1 gram detector exposure for 1 day for this data, you can already close to the theory target. Yeah.
So if it comes down and pulls out
Yeah.
freezing, is this the end of this story, or can you come up with other
So
stories?
one of my focus of talk is how can we go down to there? This is not a simple move to go down.
But if you rule it out, I mean, is that
Yeah, so
the story?
you might rule out this region, but the freezing can also go on to even smaller
If
masses.
prime is massive, right? Then you can have a freezing, and it will be many orders of magnitude below anything.
I see.
You can do experimental.
That's my question. You're asking basically, is that orange curve, can you lower the orange curve? Yeah, that's what I meant.
Far, you can lower it very, very far.
Can you lower the orange curve? I guess the answer is yes.
Well, that's model dependent.
This orange
But
curve
you don't
here-
know models.
here
Yes,
in
yes, yes.
particular, it's,
For this
it's-
particular model, yes.
It's done with FA prime being very big.
Yes, yes.
So if you go to 10 and prime, MA prime.
Yeah.
First of all, you wouldn't have 1 over Q to the
Yes.
4 Q squared enrichment in the scattering cross section. Instead, you have a suppression, and you would not have other significant constraints that you can have. And we are. And freezing.
So is this the upper limit on freezing curve?
Well,
Can you construct a model for freezing where the cross section is bigger than this?
That's my paper. Literally, well, yes, so there's an upper limit from ineffective freezing. At least the game we're playing, we're introducing one to like freedom to do that trick.
Yeah.
So you can go higher, but also I was just gonna point out that, the other parameter space you're talking about is a massive mediator. That's the one where you could really push probably quite low. For this one, in the case of a massive mediator, going lower, it's maybe a little bit. It's a little bit trickier, but they're looking.
yeah, there's also a similar projection for heavy mediator. I just didn't show here.
Yeah.
Yeah, there will be then the benchmark will be different.
Is there a limit of how far to the left this freezing line can go?
Yeah, there is astrophysical bounds or the stellar cooling bound. Actually, I will show it for the maybe a few slides later. Yeah, there's astrophysical bounds which is around the 10 keV range.
10 keV.
Yeah, 10 keV. I will show that. Yeah.
Oh, okay, so it doesn't even go down further.
Yeah.
But there are constraints on freezing from small scale structures.
And all the cosmology bound. Yeah. So the main 2 questions I want to discuss today is, given this, of course, great success, how can we proceed for the next level? So there are, of course, obvious 2 directions to go. One is go even lower, go 1 sub-MeV. One is go down, how to probe the freezing target, or even further. And so let's start with the first one. So here, I will just give a summary of the current ideas that we have to probe dark matter in the sub-GeV range. So here we discuss using semiconductors to look for ionization signals. The threshold is 1 eV, or you can use just direct ionized nuclear atoms, atomic ionization, which is threshold 10 eV. But the lesson we learn is that in order to probe sub-MeV dark matter, you need the threshold of dark matter to be sub-eV. Because now, if we stop at EV, you can only probe an MeV scale. Now the question, do we have sub-EV threshold detector to look for dark matter? Actually, there are many condensed matter systems that we can look for them. First, there's one example is if you're looking for polar materials. If your material is polar, then what you can do is if a dark matter hit that crystal, they can generate crystal vibrations. So that's called phonons. And they can have acoustic phonons or optical phonons. So given
what a polar material is.
So that means you have a unit cell, you have a positive charge center and a negative charge center. So you have some kind of dipole in a unit cell. So that can be easily, because of that structure, you can easily couple to optical phonons. You can have this kind of vibration, and that can generate easily coupled to optical phonons. So yeah, depending on what the material and what is the frequency of the phonons, will typically fall into 10 to 100 millivert range. If you have a detector look for those phonons, you can lower the threshold below EV.
Why presence of this vulnerability? Why does that help you to lower
So yeah, sure. So what's really known is that if you're looking for phonon signals instead of charge signals. So that's the key point. But depending on what kind of phonons, for example, for polar materials, they can easily couple to the models. What we have is the couple to charge, which have a dipole. That is because our models have a dark photon, so it's coupled to all the charges. So you have this kind of model. You have this has a stronger limits. This kind of, but in general, any materials would have phonons, but it's just that you have a different coupling cross section or sensitivity to dark matter, and also a different frequency range of the phonon modes you're looking for. So in general, many target has phonon modes. You just want to choose the one is good for your model for dark matter searches and how to look for them. Yeah. Yeah, there are many other exotic systems in condensed matter. If you talk to condensed matter friends, discover like superconductors or Dirac materials, which they have some. Let's here have a couple pair binding energy of mini EV. If you have a broken couple pair as a signal, the threshold will be mini EV scale. Or Dirac materials, you can open a gap in the near Dirac cone order 1 milli EV scales. So those are also ideas. You can lower the threshold down to 1 milli EV scale. It's super small. So let's complete sort of this axis with these new ideas of phonons or superconductors. So our contribution on this front is we're adding another candidate or targets for dark matter searches that is called doped semiconductors. And there are many advantages of using that I will discuss further, which also lies in the range of 10 to 100 millieV range as the phonon modes.
So if I'm talking in like a model independent sense, not specifically thinking about metallic charges.
Yeah.
Like the first example, you're really looking at nuclear, like cross sections with the nucleus. Versus the second example, you're looking at electrons.
Yes.
Are all the other examples also really probes of the electron?
Yeah, these are all electron cross sections. Yeah. Yeah, so what are doped semiconductors? And doped semiconductors can be made simply by adding impurities inside semiconductors. For example, if you consider your background semiconductor as silicon, if you add in phosphorus atoms inside it, and since phosphorus atoms has one more outer shell electrons than silicons, you can easily ionize the electron into the conduction band, and that is called a donor because you can easily donate an electron. And this is called N-type semiconductors. You can have some net electrons inside your doped semiconductors. Or the other way around, if you have borons, which have one less outer shell electrons, you can easily create a hole, and that's called the P-type semiconductors. And this type of material is actually widely used in our daily lives. because the PN junction is made by P-type silicon attached to N-type silicon, and this is a building block of the diodes that we use in our daily life electronics. So in short, the dope semiconductors are well understood, and we know how to make them and how to also the electronic properties of them. And to understand how does it work for dark matter searches, so let's look closer at the dopants, meaning the impurity atoms we add to the semiconductors, and what is the physics or the physical properties of that. In order to understand dopants, in short, it looks like we can understand it as the hydrogen atoms in quotes in a background in a large dielectric constant. How do you understand that? So here is the cartoon picture of it. So let's imagine the background lattice silicon. The background is semiconductor silicon, add phosphorus atoms to it. So phosphorus atoms have 5 outer shell electrons, and 4 out of 5 can bond it to a neighboring silicon to form a lattice, just like the usual silicon. But there's a 1 outer shell electron which is loosely bonded to the positive center, form a bond state. And we can imagine that bond state shown on the right as a hydrogen atom with a positive charge center with the electron bonded to it. But the difference is that this is a very loosely bound hydrogen atom because the Coulomb potential will be screened by this dielectric constant, 1 over epsilon. And the dielectric constant in semiconductors are typically large. For example, for silicon is order 10. Then we can estimate what is the size of the hydrogen atom by the usual hydrogen atom formula, which is alpha times ME. But now alpha should be done by this dielectric constant. ME replaced to M star, which is effective mass of the electron inside the semiconductors. If we plug in numbers, we can get like order 10 size of the Bohr radius. So it's really a big hydrogen atom. So this picture is not accurate. So you should imagine that this orbit is orbit around tens of the lattice size. Okay, then we can estimate what is the ionization energy to ionize this electron in this bound state, which is also simply by alpha squared times MeV, Me divided by 2, which you can get 10 to 100 millieV range. So that is the threshold for this type of target for dark matter searches. So let's look at how would that modify the band structure I talked about before for the semiconductors. So before talking about doped one, let's look at undoped, the pure silicon, which we know we have a valence band and a conduction band that's separated by a band gap by 1.2 eV. If we add in dopants, these impurity atoms in it, what they do is they add some discretized energy levels. For these bands, they are continuous bands, but for these are discretized energy levels inside your band gap. And for the N-type, because they are close, they can easily get electron into the conduction band, so they are closer to the conduction band. And the P-type, they can easily generate a hole in the valence band, so they're closer to the valence band. And these numbers are experimentally measured, the gaps between this energy level and the corresponding band. Yeah.
What fraction of the electrons form this weakly bound state of the material?
So depending on what is the number density of your impurities you add to it. So for what we consider is, we consider also the impurities are being sort of isolated, so they're not interacting with others. So in that sense, and also if you cool down the temperature, there's no thermal ionization of it, then all of them will be bonded to it.
So that's a large fraction of the
Yeah.
electron.
Yeah. If you have a low temperature, you're close to 100%.
Oh, I see.
Yeah.
So then your rate with interacting with dark matter is not.
Yeah. Yeah. As long, yeah, given that, yeah, at low temperature, yes. Because that's also a sort of potential background for that. So here is the cartoon picture of how our idea will work for dark matter searches. So in doped semiconductors, we have these bound impurity atoms. If dark matter hit those bound impurity atoms, ionize those electrons, the threshold will be 10 to 100 millieV, and that is a lower threshold than the usual semiconductors. And we're also looking for those charges. So the difference compared to phonons is we're also looking for charge signals, but now we have a lower threshold.
Wait, actually, can you go back to
Yeah.
the previous slide? So for a P-type dopant, I'm assuming what you're going to do is you're going to try to cool it down so everything's in the valence band, and then you look for dark matter taking you up to. new bands?
Yes. So if your electron kick it out into this new band, that means you generate a hole inside valence band. Then you can look for those holes.
Okay, yeah.
Yeah.
But so for the N-type band,
Yeah.
or for the N-type case,
Yeah.
is what you're looking for there is that like do I need to cool down the system so that
So
I get mostly in the valence, but I have some in the N-type, but nothing in the conduction band?
yes. So if you cool it down, all the charges will be sitting on these levels, will be not in conduction band, sitting on these
Yeah.
levels.
I guess I'm saying is, does that take like very precise temperature control? I need to be between
No.
those two versus to get everything in the valence band, in the
Yeah.
P-type case, to get everything in the valence band, seems like I just go to a really low temperature. But in the N-type case, it seems like I need some like.
No. So you put electron here not by thermal excite from here to here. It's just by adding those impurity atoms. They already go with the electron with it. So you adding the impurity atoms, you already put electrons on this level. But what you want to make sure is those electrons will not go to other places. Then you cool it down, then they will be bound to that.
Okay.
So those electrons were not coming from the valence band to there, because once you add those impurity atoms, you already come with electrons sitting at this band, sitting at these levels.
Okay, and I guess if I cooled it down lower, they're not going to drop down to like.
Yeah, because all these are fields, they cannot drop down. So your Fermi level is actually around here.
Okay.
Yeah.
The kind of material is essentially phosphorus, it's not the silicon. Yeah.
No. So that is how much of the phosphorus you add to it. So actually that is this number. So for this projection we use, so adding phosphorus to the silicon with phosphorus number density 10 to the 18 per centimeter cube, whereas the silicon is Avogadro number 10 to the 23. So it's like a 5 order magnitude smaller. Yeah. So it's still majority is silicon. You only add a fraction of it. But given that fraction, you already can do a lot of good things, as I showed here. So this is again projection plot with dark matter mass in MeV unit, y-axis dark matter electron scan cross section. On this curve, on this plot, I show our projection with different colors, with the solid lines, and for this type of model and this type of target, with different assumption of exposure and background. And so we can see, let's say look at this blue curve first. It's more like an optimistic one with a kilogram exposure. You have a kilogram of your target exposure for a year, and then assuming no background, 0 DC means 0 dark current, no background. Then we can probe all the way down to here and here. And here we can, and if you have only 100 gram day exposure with 0 background, you can go to orange. Now you can probe all the freezing target that is allowed by astrophysical constraint. Here you can see that this is on the 10th of keV. That is the stellar cooling bound. And this is the allowed range of freezing target. So if you 100 gram day with 0 background, you can probe all of them. So on the same curve, we see the other constraint. This is a current direct detection I showed before from Sensei, which is a stop at 1 MeV scale. There'll be other stellar bound or solar reflection bound in these corresponding ranges. Also, you might notice there will be other dashed lines on this curve. So those are other proposed targets, like this. This is the polar material. This is superconducting aluminum, and this Dirac materials. So all of this projection assuming kilogram year exposure. So you should compare all that dashed line with the blue line. You can see our proposal will be as good as or better for in some relevant range for 2 other proposals. Okay, so now this is the end of the first part.
So you're saying, since the dope, we are sitting.
If we want to go down mass, you should dope it. Yeah. So our idea is also using the similar techniques as Sensei, but just with dope semiconductors to go to lower masses.
Yeah, because you assume 0 background and every single electron excitation, you will see them. So
Yes.
you require Sensei technology to see this.
Actually, I was hoping someone would ask about the background, how good this 0 background assumption is. Actually, that is my main topic about less 20 or 30 minutes.
And
So,
also Sensei's current bounds of 1 gram day.
Yeah, it's around here. So this is roughly the background level since they have, and it's 1 gram day exposure. So that is this range here. Yeah. Okay, as anticipated. Oh yeah, maybe a quick summary of the first part is we can use those semiconductors to go lighter. Now the second part is how can we go down to probe the freezing target or even further? And are there any difficulties of going downward? Actually, there are. That is the background. That is the main topic of my second part.
Sorry, can I go
Yeah.
back to slide? So why do you choose that doping level? If I choose lower doping
Yeah.
level, will my gap be smaller?
No, so this is the number of the individual of this impurity atoms. So actually, if you want to, if you lower that, of course, your number of targets is smaller. So
Yeah,
your sensitivity goes down.
But in principle, this donor of
Yeah.
it covers a larger area.
Yes.
So I should have lower threshold.
Yes. Well, so we are basically we are hitting individual ones and then sum them together, so that we can think about this like atomic ionization, but in this semiconductor background. But there is an effect why we don't go up.
I understand.
Yeah.
Too close, it comes back to the different material.
Yes, exactly that. So yes, so that means your wave function of the electrons start to merge with each other. You form a new band, so instead of the individual one. So that calculation is very different. So we don't want to go there. And actually, there they become they call it the metal, because you have a continuous band. You populate them, then you have a lot of backgrounds there. So we don't want to go there. So this is sort of like an upper limit. But if you go down, you are not increased by the threshold, but you will be hit by the number density, the target. Yeah.
Just make sure. If I lower the doping level,
Yeah.
the threshold, the energy gap wouldn't change.
Won't change.
It's because of the material.
Yeah, molecular probably decide, because just how many of those individual atoms you have. Yeah.
What is a typical diode use? Like what concentration?
So of course they're all projection. So typically they have. So here is already the boundary of this transition. It's like 10 to 17, or that is people use 10 to 16. People use that a lot. 10 to 16, 10 to 17.
Oh,
Yeah.
like the diodes like in my phone are like 10 to the 16 or something.
I think so. Yeah, 10 to 16. Because the CCD, we also part of it is doped, which is 10 to 16 level. Yeah. Okay, let's go down to the second part about backgrounds. So what about backgrounds? So this is our like a series, our ideal view of dark matter direct detection. We put a detector with some shielding. We shield all the backgrounds. Only dark matter will come in. Great. But in reality, this is more like the realistic things. Many other backgrounds will come in, like radioactivity, defects, cosmic rays, or second emissions. So they all come into the detector, whereas the background, your dark matter signal might be a very small fraction of it. In this talk, I want to convey the information that backgrounds are very important and very interesting. And to our series, most of our series, we probably didn't care about backgrounds, because we might leave that task to experimentalists. We only care about the interesting signals. But actually, backgrounds are very important, because what we really put a constraint on is S over B or S over square root of B. So backgrounds are as important as signal. Second, they are quite interesting, because we are aiming for design some detector for dark matter searches. But actually, this kind of detectors is the first type generation of detectors in our human world that has this low threshold and low background. So it's another window to even test that mode of physics, because we haven't looked into that region before. We only need that now for dark matter searches. So it's quite interesting to see what can we get. And so here is the summary plots. So now, as I showed you, there are many experiments has been built and taking data. The point now they see a lot of events. It's not because they see nothing and put a constraint on it, but they see a lot of events, but they don't know what is the origin of those events. So that's why we call it anomalous events. So here are the summary plots from the Access workshop last year, which list all these kind of dark matter detection, sub-GeV dark matter detection experiments, where x-axis is energy deposit in the unit of keV, y-axis is event rate in this unit. So you might note, so by the way, so this plot is already, so this low energy range, we already sort of cut off away this known high energy backgrounds. So what we expect on this plot is nothing, is zero, or dark matter. So our serious wire on this is 0 or dark matter. So that's what we expect. But this is what we see. And then you might wonder, what are these like peculiar features? Like, especially there are some kind of blowing up near the left end, meaning near the threshold, like low energy. So what is this funny feature? So you cannot expand by other known sources because they already removed the known high energy background. So what are those? Maybe your first reaction is, could that be dark matter? So actually people are very excited at the beginning and they propose as a dark matter explanation of all those events, but very rough estimation, but they said one model can explain all of them. So people get very excited. But soon after that, when people did more refined calculation of the model they proposed, yeah, it cannot explain those events. So since our work, which is shown here, we point out there are several unexplored low energy backgrounds that could contribute to all those events. And after our work, many more theories will come in to study more possibilities, and also followed by experimental groups to test our hypothesis in the real labs. So it's still now it's still an ongoing effort with both theorists and experimentalists to find out what is the real physical sources to these events. Okay, so now I want to, in this talk, I'm going to give you a sense what are the new backgrounds, unexplored backgrounds we point out that could explain those events. So in short, we give one example. It's Cherenkov radiation can mimic dark matter signals. Why that's the case? So here is the cartoon picture of the detector environment. We have our detector sitting in some copper vessel with some heavy metal shielding, with some holders and cables. If a high energy charged particles, let's say electrons or muons, either coming from cosmic ray or radioactivity, hitting your detector, holders or cables, because all of them are dielectric, they can radiate Cherenkov radiation. And Cherenkov radiation in these typical cases are low energy or the EV scale. So those radiation later being absorbed by the target, by the detector, will generate these low energy events. And that will be responsible for those anomalous events. And to be specific, that the Cherenkov radiation in detector can expand the sensor access. Cherenkov radiation from holders will contribute to supersynthetic sub-GeV access. So what are Cherenkov radiations? You probably learned that already, but just to remind you, or one slide to remind you what are Cherenkov radiation. So Cherenkov radiation can be radiated when an incident charge is moving faster than the speed of light inside a given medium. And this is a similar phenomenon as airplane is moving faster than the speed of sound, then you generate a shock wave. So that's a similar feature. So here is the cartoon picture of that. When there's a charged particle passing through in this direction, you will radiate Cherenkov radiation with a specific angle, and that angle is set by this formula. And the condition to generate Cherenkov radiation is your velocity should be large enough, and it's given by this formula, where V is the incident particle velocity times the real part of dielectric constant greater than 1, where dielectric constant is a combination of the refractive index and the extinction coefficient by this formula. So the real part, if your material is sort of transparent, your K is small, then what you have is epsilon is n squared. So you can rewrite this as V greater than 1 over n, which is basically that is the speed of light inside the medium. So this is the condition for the velocity. And there's also a classical formula to estimate what is the rate of the Cherenkov emission, which is given by this formula. So the leading order is alpha. Alpha is the electric fine structure constant. And so now I give you one concrete example. This is from sensor collaboration. How can this Cherenkov radiation contribute to the events they observe? So let's give first a brief introduction. What is sensor experiment? Sensor is using CCD, especially a skipper CCD, to look for electron-hole pair ionization. So here's a cartoon picture. If you have a piece of CCD, which is a piece of silicon, divided by many, many pixels. If dark matter hits the CCD in one of the pixels, generate electron-hole pairs, and then there is an electric field across the surface of the CCD. So the electron and holes will be drifted to opposite surfaces, and later that being read out. So CCD can read in which pixel, if there is a dark matter event happens, has and how many electrons inside that pixel. So that is what CCD can measure. So the expected dark matter signal in this case will be one or few charges per pixel, because we are looking for light dark matter hitting silicon, generate one or few, very few charges per pixel. So that is our expected dark matter signals. Because dark matter cannot drop a lot of energy in it. And for this range, we care about. So this is expected dark matter signal. Okay, so what about the real data? So here is the real data from Sensei. Since Sensei is using CCDs to look for dark matter, and we use CCD also in our electronic cameras. So what is the data from Sensei is the image, and this is the image, the real data. And they use Sensei, this like 1 gram active mass exposure for 1 day. This is what they got. So we can see many patterns on the image, and we can, by looking at the patterns, to identify their physical origins. For example, you see these bright, long tracks are likely coming from cosmic muons. The cosmic muons will be penetrating the whole CCD without stopping. And the white blobs are likely coming from X-rays, or shorter tracks are coming from high-energy electrons. So the expected signal, or in other words, normally what they found, is the little white dots all over the places. I don't know whether you can see them, the little white dots. So the bright and the brightness of here is how many electrons per pixel. If it's bright, many electrons per pixel. But there are kind of very dim dots, so that means you have 1 electrons per pixel. And that is the anomalous event, which is also expected dark matter signal region. So that's why people got interested why there are a lot of these events. So given the short of time, I will just quickly go through this plot, is how well the Cherenkov events behave and generate this distribution of 1 event in Sensei. And let's imagine if a charged particle penetrating your CCD generates Cherenkov photons with some specific angle. And these photons will travel to some distance and then being absorbed. And that distance is determined by the mean free path of photons inside the silicon, which is shown here, or the absorption length, as a function of frequency. So yeah, let's first look at what is the sort of energy spectrum of those generated Cherenkov photons inside silicon or germanium, which is in the color band here. Because there's a threshold to generate Cherenkov photons, and that threshold is the V times the real part to be greater than 1. That means only your epsilon to be greater than 1, then it's possible to generate Cherenkov photon. That is only in this range, which is a few eV. And if you look at how far the photon can travel, and most of the photons above 1.4 or 6 eV, they cannot travel far. They'll be quickly stopped in the neighboring pixel. But for photons near the band gap, they can travel quite far, and they will lose the connection with the high energy tracks. They will be distributed all the way around in the picture. So that will contribute to the events we see. Okay, so these are just words, but let's look at our simulation. So we did a simulation, put what we found into the simulation, and to see what we get. So here is the real image I showed you before. Here is our simulation, given the spectrum they measured, and we simulate high energy tracks, only high energy tracks, which I can roughly mimic all these bright tracks. But of course, it cannot mimic all these like little dots. If then we add Cherenkov radiation, then the situation will be more like what we see in the left. So these orange dots are from Cherenkov radiations. And first, we might notice most of the orange dots will follow the blue dots, which makes sense because many of the Cherenkov photons cannot travel far. They'll be stopped right away. But there are other like these orange dots like flying around, which is far away from all of these tracks. So those will contribute to those like the uniform distribution of this sort of uniform distribution of these white dots. So that contributes to the excess events. Okay, to draw like a one-to-one comparison with what Sensei found. So let me introduce one like analysis cut that they use, because later they will project their results with this halo mask radius. So they have an analysis cut called halo mask. The idea is you identify a pixel which is very bright, meaning many charges in it, likely coming from high energy events. Then you draw a circle around that and remove all the pixels inside, just to remove the impact of the high energy events. And you do that for all the high energy pixels. If it's a track, you do that along the whole track. Now the question is, what is the radius you choose? And they vary, and then they will see how the data looks like by varying the radius. So here is the halo mask radius in the x-axis in unit of pixels. Y-axis is one event rate with a gram day as a unit. So here is the real sensor data. Clearly, we see there's some correlation of high energy events and one events, because at low radius, meaning the event is closer to the high energy track, we see more events. And if it's away from it, we see less events. But even if it's more than 60 pixels, which is around like 1 millimeter above, with the people see data streams might be flat out. So it not drop to 0, it just flatten out.
Were they doing this specifically to get rid of Cherenkov radiation?
No, so they just get it to see, because they want to find what is the optimal radius to cut and to project this scientific result. So they found this behavior. They don't know what's happening here, but they put a cut at 60 pixel. So they put a cut at 6 pixel. They only use the data which is more than 6 pixels and to project their result.
Okay. They just saw there was some correlation. That
they didn't know it, but they just cut it away, and then that's what they report in the result. So what we try to say, whether our explanation can reproduce all these features. And here is our result from our simulation for Cherenkov events. So that is in blue. So first we see that we can reproduce the shape as a function of the halo mask radius. We also see this correlation, and we can explain the shape. But unfortunately, as you see, there's a gap between these two. So we cannot match all of these events by Cherenkov radiation. So what are the remaining things here? So what we can do is, if we trust our simulation and we subtract the real data from our simulation, what is left is about 2/3 of the total events, which is spatially uniform, meaning that it's flat in this x-axis, the spatially uniform. So it will be Cherenkov plus some uniform background. They can reproduce the one event what they observe.
For your Cherenkov events,
yeah,
if I extend to 120 pixels, what happens?
Yeah, so it's also flattened out. So it's flattened out here, because that is more will be limited by the size of the detector. So you might hit the boundary of the size and then bounce back.
Or if I admit there are random dark events as a hard uniform floor, I will move up in the curve. Are you aiming at predicting the full black curve using Cherenkov?
No, not using Cherenkov.
Yeah.
So that's why I'm saying there are other sources which contribute to the uniform flat background, which is not Cherenkov. But currently we don't know what are those, so we cannot simulate them. But what we propose is, we see there's a uniform feature, and there are possible sources to them, like from surface dark current, because there are likely defects at surfaces in the detectors. They can generate surface dark current or charge leakage, because we need to add the electric field at the surface. There could be charge leakage at the surface. So those are possible sources to these flat backgrounds. So what we learn from this? What we learn from this is that Cherenkov can likely to contribute to order 1 fraction of the observed events, which can produce the shape, which is very promising. But we see there's kind of like a gap between the Cherenkov and the rest. If we, in the future, if we put our detector in a much cleaner background, so since it now is at 100 meters underground, so it's not very clean, but it's clean but not very clean. So now they move it to slow lab, which is much cleaner. So by doing that, the Cherenkov events will go down because it's initiated by high energy tracks. If your high energy events go down, this will go down correspondingly. But this spatially flat path will not go down because it's intrinsic to a detector, not to the high energy event. So then the question is, if we really want to improve the detector sensitivity, because this is 2/3, which is a huge amount, how can we improve our detector sensitivity? Then the question is, how can we reduce this uniform intrinsic dark current? Yeah.
So here you're focusing on about your
super CMOS, yeah. I have a back slide for that. Maybe let me just go to this point, and then I'll go back to that in the Q&A session. So we propose the idea to reduce this surface dark current intrinsic to detector, and we call it like a dual-sided CCD with a collaboration listed here with both theorists and experimentalists. To understand that, so let's first introduce how the regular CCD works. To give a closer look at regular CCD. So here is a regular CCD, but we rotate it 90 degrees, and this is the front side, this is the back side, with some electric field across it as negative and positive. CCD is designed by some doping inside of between to generate electric potential shown by this shape here. This is electric potential. Once you generate electron hole pair inside the bulk, holes will be drift to the bottom of the potential because positive charge will be stored here. And then electrons, in this case, will be lost to the gate because there's a contact, you're lost to the gate because there's no place for it to store. So in the regular CCD, for this type of regular CCD, we only store holes, and that we only read out holes, and that is how the regular CCD works. So in short, regular CCD connect only one charge. You can also sort of do the opposite doping to get electrons, but for the regular CCD, they only connect one of the charges. So that's the point. And for our idea of dual side is we make the front side, or back side similar to the front side, but also modify the doping of the CCD to generate the potential maximum near the back side. So now we have a potential minimum and maximum. By doing that, electron pairs in the bulk, well, we can store holes at the front and electrons at the back. So we can connect both of the charges. So that's the key idea of the dual-sided CCD. Then the question is, why are we doing that? Because let's reach the why this is meaningful. Let's look at how the surface dark current behaves in this type of detectors. So surface dark current, by definition, you generate charges at the surface. If you generate electron hole pair at the front surface, only holes will be connected, the electron will be lost. Or if you have electron hole pair at the back surface, only electrons will be connected and holes will be lost. So the short surface dark current will only show up in one side of the image, whereas the real dark matter ionization event in the bulk will show up at both images in the same pixel. So that's the key point or the distinction feature between dark matter events, bulk events with surface events. Then probably also notice that we can use this type of coincidence or correlation to get rid of surface dark current. So I can just show you, give a cartoon picture of it. So let's look at what is the current level of dark current measured by Sensei. So there is like a 450 per gram day of the dark current rate. If you translate into this unit per pixel per day, if we exposure for 1 day, for each pixel, there's 10 to minus 4 times to find the charge. So this is the current Sensei rate. It looks already small, but it's still big for dark matter point of view. Given this rate, let's say given this rate, then if we have a dual-sided CCD, what can we do? What can we improve? So this given this rate, that means, and also assuming it's coming from a surface. At the front surface and back surface, we have two images from dual-sided CCD. Each of them has a random distribution of those events of that rate, and front and back. So the probability of finding two charges accidentally at two surfaces in the same pixel is this rate squared. Because you find one is 10 to minus 4. To find another one in the same pixel is another 10 to the 4, 10 to minus 4. So by random coincidence of the surface events, finding the same pixel is 10 to minus 4 squared. And you can, so that will mimic dark matter events, where other random events will be just randomly distributed. They will not correlate with the same pixel, so we can get rid of that. So then the dark current rejection rate is 10 to minus 4, if it's ideally.
Yeah, but we don't know if this uniform one electrons are from dark current. If they are from other particle origins, they will be correlated. You will have no rejection.
But the assumption is there could be other source, but if it's coming from surface, then all of this will work.
I understand.
Yeah.
It's coming from external sources, they will be uncorrelated.
Yes.
come from any other kind of scattering or
Every other scattering in the bulk, then they will be correlated. Yes, but then it's so far we don't find another convincing process in the bulk that can contribute to this rate. Whereas the only but surface is rough and it was hard, it's likely to generate some background, which of this size. But if it's surface, they can reject. I agree. If it's bulk, we cannot reject. But our assumption is if it's surface, and it's likely coming from surface. That's our point. Yeah.
Even this dark current rate, where would that show up on the plot you were showing for the shrink off radiation?
Oh,
Like,
yeah,
How many events with that?
So that is the so that is this rate. So that shows this gap.
you move black line down.
Yeah, you
I'm saying like, can that dark current rate actually explain this?
yes,
gap?
yes. So that is the number we chose. That is if you give that number, our hypothesis is Cherenkov plus flat background can explain how we sense it, and we can predict what is the number of that flat background, and that flat background is that number 10 to minus 4.
Oh, the dark current, that's not measured.
It's not measured, but it's roughly this number. It's because it's order 1 of the sensei observed.
Right. Okay.
Yeah.
It's the amount that.
Yeah, we need to run this. Yeah. Okay, so that we have a 10 to minus 4 rejection, but that is an ideal case, assuming no diffusion. Diffusion meaning if we have a charge generated in the bulk, they will be drift to the surfaces, but they can also go sideways. You may not go always perpendicular to the field line because they can scatter with other other atoms. They can go sideways. So that's called diffusion. And if you diffuse to 1 neighboring pixel or 2 neighboring pixels, this dark rejection rate will be worse because effectively your pixel size is bigger. So that's why you are more likely to have coincidence events. So that's why the rejection will be worse. Now, I want to discuss this plot might be what we really care now is how can we improve, once we have this, how can we improve on the dark matter searches? So here is a plot with the x-axis the mass, and the unit MeV, y-axis is the dark matter electron scattering cross-section. Now we assume it's a 10 kilogram year, like ultimate goal of the exposure, very large exposure. So the green line is using standard CCD, current technology of CCD, but just extended exposure to 10 kilogram a day. That is what we observe in the future. We predict in the future. Notice that, so this shaded region is from current exclusion. We can see at low mass end, even if you have a 10 kilogram a year exposure, the bound will not improve. So that is because in this region is background limited. Once you have larger exposure, you are observing background again and again, so you will not improve dark matter sensitivity. So in this, that means already dark matter background limited. But once we have a dual-sided CCD with 10 to minus 4 improvement, we can really improve at low mass into 4 orders of magnitude. But high mass, we have a less improvement because here is not really background limited yet. So, but most will be prominent will be the promising will be the low mass range. We have a 4 order magnitude of improvement. And just compared to our serious view of the background, would be no background, so it would be this curve. So in order to really touch this curve, we really need the technologies what we propose to beat down the background to go down to improve the detector sensitivity. Okay, so given the time, probably I can skip or just mention that we built this detector aiming for reduced surface dark current, but there's a byproduct. We can also generate improving timing sensitivities of the regular CCD. Because regular CCD, we really put them for long exposure and then read out. Anything happen within that exposure time, we cannot tell which happened earlier, which happened later, because everything is encoded in 1 image. But now if we have 2 images and go in opposite directions, we can improve the timing resolution. Let's say, given some number, I have one to go from 1 second to millisecond. And this is one concrete example that we can add in some kind of timing information to it. So you have some real situation at time 0, you generate this event, time 20 and time 60, you have this event long tracks. So by using regular CCD, you only have 1 image, let's say on the front. So you cannot tell which this one happens at the same time as this one, because you only get one of each image, or later. But by using the correlation of the front and back, you can really tell, yeah, this happens first, this happens later, and we can use the correlation to give time labels for all these events. So that is one example we can also do with the dual-sided CCD. So dual-sided CCD, we are very excited about it because it has also not just dark matter, also astrophysical applications. You can look for some rare events for astrophysics and for this millisecond timing resolution. That would be really good. Now we already form a collaboration with theorists and experimentalists, I showed it before, and we also submit a proposal, and we really want to get the experiment done. And now it's moving fast, so we're also very excited. We're hoping within 2 or 3 years, we can have this detector being built and also have some first scientific tests whether we can really reduce the background as what we expected. So stay tuned, and exciting result will come soon. Okay, now that's all about today. Now give you a summary, and probably not read all of the words. Is that the sub-GeV dark matter detection is very exciting, and it's an ongoing rising project, rising field. And so it's welcome that you can propose your ideas and work with experimentalists to realize them in labs and put a constraint on this plot. So in this talk, I introduced we can probe sub-MeV dark matter using dope semiconductors. In order to probe freezing target or even further, we need to understand backgrounds. And we propose that Cherenkov radiation could be one of the backgrounds, but there's still some kind of unknown intrinsic surface dark current. And we propose using dual-sided CCD can reduce some of those backgrounds. Thank you. I'm happy to take more questions.
Time for red box or questions.
Yeah.
Non-dark matter applications of your dual CCD?
Yeah, so I mentioned a little bit is the astrophysics of the astrophysics. So if you're looking for some rare events, and meaning, so currently, for astrophysical purposes, we are looking for a source for a very long time. We can accumulate light. So if you have some background, eventually your signal will be over a background. So that would be great. So you don't need to have very low background devices. But once you have some rare events, you only see like a pulse once. And then if you have already buried under your background, you will not dig that out. So one of the idea we can apply to astrophysics for some rare events, and also we have the millisecond time resolution, then that'll be sort of good for those applications. Yeah.
Sorry, it's called dual CCD?
Yeah, dual-sided CCD.
Yeah, is this going to be this proposal that you mentioned? Yeah. Is this going to be a future iteration of Sensei, or is this now?
No, it's a different one. One, because it's a different CCD compared to Sensei. You need to really redesign it. Now we really form a collaboration with experimentalists first to design it and to build it so this is a new detector. It's a new detector. Yeah.
What's it going to be built?
Sorry. So now, we collaborate with MIT Lincoln Lab, so they know how to fabricate from like silicon wafers to the CCD. So they know how to build the CCD, regular CCD, and now as we told, contact with them, they found it's not difficult. Probably it's not so difficult to use the normal techniques, but just to, or what you use from front side, but apply to the back side. You just do the two sides with similar technology. So in principle, it's doable. That's what they said they can do it. They tried to do it. And so, but just as I showed before, by looking at the picture, there's no difficulty of just doing like what I showed on the right-hand side. It just possibly before people didn't realize that's meaningful or is useful. So that's why they taking the simpler path. They only do one side, and then of course it's simpler and cheaper than doing both sides. Yeah.
Oh, so these so in the second half of the talk, you're talking about these one electron backgrounds. So you're focused mainly on Sensei.
Yeah.
But
yeah,
you know, obviously this background you showed early on, it's seen in a whole bunch of different experiments.
Okay.
I think you mentioned a little bit about Cherenkov
Yeah.
and maybe super CDMS, but is the idea that that all of these other experiments, I mean, it seems like your analysis is very specific to Sensei.
Yeah.
Is the hope that all these other different experiments might be seeing similar effects, or
For super CDMS, probably yes, but for others, probably small fraction. So that's a short answer. But let me, since also you have asked a similar question, maybe some people also interested in the audience interested in super CDMS experiment. So let's give a brief introduction of super CDMS GeV and how our idea will explain those events. So here is the detector. Looks like the cartoon picture is here. So you have a silicon detector. That's the active detector sitting in between. They are clamped by two of the PCB. PCB meaning printed circuit board, and they just hold some electronic readouts on these two PCBs. And this is the roughly detected environment. And yeah, so this is what they see is also another view of what we see before. They see so these spikes are corresponding to 1, 2, 3, 4, 5 events. What they measure is the phonon energy instead of charges. But what they do is if you create electron hole pairs inside in between, and you add a voltage, let's say 100 volts across the target, the phonon energy will be integer number times the volts, because that is the total energy released inside when the electrons crossing the whole electric field. So if you 1 electron times 100, this will be the peak here. 2 electrons times 100 will be here. So that's just 1, 2, 3, 4 digitized number of electron events. So that is the number shown here. And they verify that is independent of the voltage. And so they have hypothesis that for the 1 event rate likely coming from some charge leakage, but they have no explanation of the rest of the events. So how does Cherenkov hypothesis work in this case? So it will be slightly different than Sensei is once the charged particles directly hitting the detector, these type of events will be vetoed because super CDMS is a fast detector. They can you will see a charge, high energy charge together with low energy events. You will not tell whether there's any like low energy events because it's all buried under these high energy events. They have a timing resolution. But once your high energy track hitting other hardware inside the near the detector, for example, PCBs or connectors, they can radiate Cherenkov radiation and then bounce back to hit the detector. Because this high energy track will not be recorded by the detector, so you are not using timing resolutions to reject them. So those will be contribute to the excess event. And we did an estimation. So why we didn't show that, why I didn't show the example before is we don't have a very concrete or confident estimation about the events because we don't have enough information to simulate them because it's a very hard process. But what we can do is we can estimate it. We estimate that assuming, there's one important quantity which we don't know is the efficiency of generating Cherenkov photon being recorded. What in the end we evaluate, and then until this number, we can fit the spectrum like this very well. So this is of course not a proof of anything. It's just given this fraction of efficiency, we can roughly reproduce all the observed events by super CDMS. So this is likely like one parameter fit the 5 points. It's likely to suggestive that this could be one of the backgrounds. And of course, notice that we cannot explain the 1 event rate because that's way up there. But this could coming from charge leakage is a different source. So yeah, that is our it's not not conclusion saying that this all coming from Cherenkov, but it's suggestive. And
But can we reject those events?
but there's a simple way to do that is by removing or smaller fraction of the PCB, use smaller amount of PCBs, because that is where you need to hit those materials to generate this event. Actually, the interesting thing is that I heard probably super CDMS has already done some work to reduce the PCBs and they see a reduction of the events. So that's sort of a suggestive that this will be likely coming from this Cherenkov events. Yeah. Yeah, the simplest way just to reduce the amount what you use for these PCBs. Yeah.
Aren't there materials that have like dielectric constants close to one? Like they try to use those instead?
Metal is one of them, but there's other things is the metals has other issues because have free charges. They can also leak into the detector. But actually there are ways to get rid of that is like Crest is another collaboration. They use scintillators to look for dark matter. They also put the scintillators on their holders. So every part inside the near detector, they put a detector on it. So once high energy particles even hitting your holders, they can record that. You can also use timing information to reject that. So that's how Crest did. So there are several ways to reject them. So that's the way the Crest did. So actually, maybe it's also worth to show you one of these. Yeah, this summaries table of other experiments. Like, so we are more likely that since and super limits, our Cherenkov will be the dominant source because they are either at the surface or not so deep underground, where they have a large ambient background. So it's likely that a Cherenkov event will be source for those anomalous events. Whereas for Crest and otherwise, they are much deeper underground. So our Cherenkov contribution will likely to be subdominant or vetoed already for Crest. But they also saw some excess that might coming from other explanations. For example, one explanation is coming from crystal cracking or microfractures. So your crystal is not perfect. You have some defects inside it. And now as time moves on, that will generate phonons. And that will generate those backgrounds that Edwards and Crest see. Yeah. Thank you.